Okay. So there's no questions. Today we're going to get deeper into displaying data. That's what section 10.1 is mostly about. Collecting data, displaying data. 10.2 is all about analyzing data, where we start doing calculating stuff like the average, stuff called the median and the mode, and then we start doing a little bit deeper stat stuff. Calculating the spread of data, how spread out the data is. So as a teacher, I remember last semester, I think, those of you who had me last semester or before, after a quiz or a test, I think I put the average on the board, but I also put a number that represented the spread, if I remember correctly. So we're going to talk about how to calculate how spread out data is. Okay. I'm going to use this one. Yes. This way. Okay. I think we got up to, I think the last thing we did was stem and leaf plots, is that right? Yes, thank you. I appreciate memory help. So let me talk about stem and leaf just a little bit deeper for a second, and then we'll do some other visual displays of data stuff. Can somebody just tell me, if I have a collection of data, let's say 125, 128, 129, holy shit. That's okay. Now that I'm using this other thing, I forgot where everything is. Let's try to write that in English, that'd be amazing. 125, 128, 129, 130, 151, 152, 156, 158. Sure, okay. Can somebody tell me, what could the stem be for this? So we have stems and we have leaves. Does it make sense for the stem to be 1? Why not? They all have freaking 1. So that would just be 1 with the whole data list. And what's the, can somebody tell me, I know you haven't lived with stem and leaves very long. Some of you guys might have taken statistics, so you know stem and leaf from before, but what's the main purpose of creating a stem and leaf graph? Stem and leaf plot? What does it seem to be the purpose? What do I want to do if I collect a lot of data and I want to give somebody a visualization of it? What am I trying to show them? If I just make the stem 1, I'm just going to have 25, 28, 29, it's going to just be this list. Is that going to show what I want it to show? Can somebody figure out what is it that I want to show? Yes?
The trends of the data.
Trends, good. And one kind of way to get a trend is to see how distributed the data is. Where does it seem to be clustering? Where does it seem to be gathering? Is there a place? Is it uniform, which would mean every stem has the same number of leaves? That would be a uniform distribution. Or is it even, what's this one called? I should have wore that shirt, that's okay. Anybody know if I have a distribution that looks like this?
Oh,
Bell curve, right? So as a teacher, you should start to know, if you don't know yet, the idea of the bell curve. It's also called a normal distribution. Yeah, because, well, we'll talk about it a little bit later. So I want a quick way to visualize the data that can show somebody how it's kind of distributed. Is it one of those things? So using 1 as a stem here would be silly. Can somebody give me something better to use as the stem that would then have leaves coming off?
12.
Good. So I could have 12, 13, 14, 15. Now real quick, are there any 140s in this data?
No.
That doesn't mean you just don't put it, because that's information. An empty spot is information. So you don't not represent information. Don't skip any possibilities. So what goes after 12?
5, 8, 9.
Okay, gas. 3, 13 I mean? 0. 14, poor little dude, and then 15 gets 1, 2, 6, 8. So that's a nice quick visual. I can see the data seems to be sort of, you could even call it, let me see if I can hazard this, bimodal a little bit. You got most at the bottom and another most at the top. Most is at the top edge, yes? So it seems to be clustering in the 150s. So there's several things I can get, and that wasn't difficult to make. So as a person looking at this, I can get a lot of stuff from it. Now, let me ask you this. If I did not show somebody the data, and I just showed them this, are they going to read it the way I want them to, necessarily? I don't know if you guys understand what I'm asking. How do they know that 1, 2, line 5 means 125? They don't know. It could mean, so 1, 2, line 5, that's right here, yes? Wow. That could mean 12.5. It could mean 1250. It could mean 0.125. You guys understand what I'm saying? So what's interesting is, I need you guys to really be with me. So what is this course supposed to mean? 125. So this is something the book doesn't really talk about, but I want you guys to know that is the key. Sort of like having a scale and a map. You just have to put it once and then I know how to read the map. You have to give me a key so I know how to read the freaking thing you gave me. Now, real quick, don't do this, but just watch. If my data would have been this instead, you guys see what I'm doing? I'm the evil math god, and I'm dividing everybody by 10. Yes? Would my stem and leaf plot have changed at all? 12.5, 12.8, 12.9. The stem and leaf, this actual thing right here, would it have changed? No. What would have changed, of course? The key. I would have made the key, shapow, and then they know how to read it. So, a given stem and leaf plot could represent a lot of different kind of data. The key is what tells me what it represents. How you guys feeling? You guys all right? Okay, it's no longer money. You don't have that excuse. We're deep into it now. Okay. All right. One other little thing about stem and leaf plot. What if so let me recreate this. Dadgummit, Jeff. If I could just plan ahead, that'd be amazing. So 589, jumbo 1, 589, what was this? 0, 1, 2, 6, 8, okay. And don't, without the dots. So 1, 2, 5 still means 125. Okay. All right, so that's the same thing we just had a second ago. I just put extra shit on there for some reason, yes? So what if I gave you a second list of data? So let's say this is recording, does anyone ever bowl? You guys ever bowled before? Yeah. Yes? My little brother, I was about to do this, but it's actually this. He bowls professionally, not professionally, but he does. So he's got like 6 different bowling balls depending on the conditions of the lane and all this kind of shit. I just go and I'm like, this is good. So his average is like 200 something or whatever. I'm happy if I break 100, so. Let's say this is bowling scores for a amateur bowling team. What about if we have the red team down here and their scores look like this? These little overperformers down here. Right? I think some of you guys might see where I'm about to go with this. By the way, what am I doing that's really nice with my data? I'm giving you the data already sorted, yes? So it makes this quick. What I'm gonna do is I'm gonna build a 7 leaf going that way for the other set of data. So next to the 12 would be nothing, of course. What would be next to the 13 going this way?
1.
Yeah, there'd be a 1, 4, and then next to the 14, 8, 9, 9, and then next to the 15, yeah. So 2 things stand out. The red team's a little bit smaller, but they seem to overall be better. Not even, now notice, the blue team has more people in the 150s. This is cool, I can't even claim that I did this on purpose. What is it about the red team that tells you that they're sort of better if the blue team has more people in the 150s? Describe the red team for me. What's different? Why is the blue team a little worse on the whole?
Is it consistency in a way?
Say again?
Consistency?
Consistency, right? Isn't the red team a little more consistent? They have less variability. The blue team has a huge, like, this one dude at 130 is saving the middle, otherwise the middle is all empty with me. Whereas the red team's kind of clustered. So do you see how the spread of the two data sets is different? That'll be in the next section. We'll talk about how to calculate the spread of data. You guys still with me? Okay. Alright, so you can have a stem and leaf plot by itself, you can have two stem and leaf plots. The book doesn't really talk about the key, but it's so necessary. I need you to put a key whenever you put a stem and leaf. Because that's how you communicate to people how to read your stuff. Okay. Boom, boom. So going back a step. I think I said this word, and by the way, if I ever leave something behind you didn't finish copying it, let me know. I can't remember if I said this. Dot plot. We haven't done an example. The book calls this a line plot. For some unknown frickin' reason. They do say dot plot in the write-up, but in the homework they ask you to make a line plot, which is very confusing to me, but we'll be okay. And I'll show you why. So, let's do everybody's favorite thing. Let's watch Jeff make up some freaking numbers, okay? Okay, that's exciting. One thing about this data that's different from my earlier data, what's one thing you notice about this data?
There's more repeated numbers.
Say again?
More repeated numbers.
More repeated numbers, exactly. So dot plots and line plots are useful for when there's more repeats in your data. And you'll see why very quickly. If there wasn't any repeats, you will see why this won't be the most useful. It's still okay to do, but it's a little more useful when you have some clustering going on. The great thing that a dot plot does, it shows you where the data seems to be clustering. So if you just make a number line, start at 14, that's crazy. Where'd I go up to? 30 freaking 5? Shit, Jeff. All right, hold on. Let me adjust. Is that what I want? No, that's what I want. Okay, we can do this instead. Go away. Okay. So the reason why the name dot plot is a better description for this is because I'm literally going to put little dots above where the numbers are. So above where 14 would be, I'm going to put two dots stacked on top of each other. So above 15, I'm going to put 3 dots. Above 20, I'm going to put 3 dots. Above 21, I'm going to put 1 little dot. 22 is going to get in there. Dadgummit. Don't tell me you died. Did you die? No, you didn't. What else did I say? 21, 22 gets 2 dots. 35 gets 1 little dot. So you can see how this shows me, and again, if there were no repeats, you could still kind of see where the data seems to be clustering. You can very quickly see where the data is clustering. This would be even more useful if my data list was kind of really big. This data list is really small. Did I really need to make that? I could just see from the numbers where it's clustering. If I had 800 numbers, holy shit, give me a picture. I don't want to look at that. You guys know what I mean? And then I can very quickly see where it's clustering. I keep saying this word cluster. It's really good. Here we go. This has happened to me. If you guys make a test and you get, let's say you're teaching 8th grade or whatever, and you get like 30 students that got exactly a 76. I don't know, you guys don't have, do you understand how that would be a little weird? Almost every time this ever happened to me, there were specific problems that almost everybody didn't understand. So they basically lost, and then some people were different because they might have gotten more wrong on other stuff. You guys, but like this huge group was 76, and I'm like, what the shit? So then you go back and you go, oh, almost every single person missed 1, 4, and 7, and 8. Holy shit, I didn't teach that well. Damn me, you know? You guys come with me? So this idea of where things are clustering is important. Okay, that's all. So dot plots are your friends. In the homework, they're going to call them line plots. Do you guys see how this? I see why they call it a line plot, because it's a number line. But what is the main thrust of the picture? Dots. So of course you call this thing a dot plot. Okay. If you like line plot, go ahead, use it. You're just weird. Okay. What kind of graph? I think I put this up here before. Let's say that I survey people, and how do I want to say this? I don't know. People that are less than 21s, 40 said yes, and people that are at least 21, 22 said yes. What kind of picture could I create to show that?
It's like a bar graph.
Beautiful.
I think it's called.
I love it. And see, that makes as much sense as the dot plot. The main thing with the dot plot is little dots. The main thing with bar graph is freaking
Yeah.
bars. Yeah. So I would have less than 21, greater or equal to 21. And then here's where you gotta be really careful. The y-axis. The x-axis is not really an axis. It's just labels, categories. It's not really a number line, you guys with me? Just categories. The y-axis is gonna be numbers, yes? Therefore, its scale better be frickin' consistent. Don't go 10, 11, 20, 38, 41, holy shit. So, can somebody give me a decent scale for my y-axis so I can represent that data? You know what I mean? Do I wanna go by ones? Thank you. If you said that, I would reject that. Should I go by 20s? No, so what's a good? 10, kick ass. So if I go 10, 20, 30, 40, where am I going? Yes, that's perfect. 10, 20, 30, 40. And by the way, if I had me as a student in this class, I would say, Jeff, get some frickin' graph paper or something. Holy shit, dude. Look at that, that's horrible. So try to make your scale consistent. Number saying yes, and then you just make your bar. So your bar for less than 21 goes up to 40, and your bar for greater than 21 goes up to 22. Okay. And of course, we're doing this by hand, so it can't be perfect, so you just kind of eyeball it. All right, nothing major. You guys have seen bar graphs, you know how to read them. Creating them is not that hard. Let me ask you this. What if I wanted the y-axis, so this is the, let me put down here ages. What if I wanted the y-axis to be percentages? How can I do that? What percentage of the people I talked to less than 21 said yes? So whatever question it was I was asking. How many total people did I talk to?
62.
And how, out of those many, how many are less than 21 that said yes? Out of those 62, how many are less than 21 that said yes? 40. So it'll be 40 out of 62. And then you just figure out what that percentage is. So what would that be?
A little over 2/3.
Yeah, it's like a little under 2/3, like 0.65? So we have a calculator?
Yeah, 64.5%.
Yeah, thank you. And so of course, so that'd be less than 21. So greater than 21 would be 35.5%, the rest of it, yes. And then you would just make your scale based on those numbers instead. So you could do it either a total number of, or you could do it a percentage of. And normally the percentage is better. Okay, so very quick word about how to mislead people. So very often you'll see somebody say, oh, the disparity in pay is not that big. I mean, look at this, look at that. Look, that's not a big disparity. And that's because they've chosen their scale to minimize the effect. Or the other way around. If I want to say like, so I haven't shown you the scale on purpose. If I want to say like holy shit, look at these people versus these people. Oh my God. But then my scale is 61, 62. Do you see what I'm saying? Now, can anybody see an immediate problem besides the fact that you can barely read it? An immediate problem with my y-axis scale?
It's too close together.
How do you mean too close together? Ah, good, there, exactly. It starts at 61. It does not start at 0, therefore the heights will not be representative.
Yeah.
If I started this at 0, those two bars would be almost the same height, yes? This happens a lot more often than you realize. And not enough people understand what to look for, so therefore they make decisions based off this incorrect perception. As a math guy in today's world, I go insane every day. So you guys are going to be out there doing the good stuff, trying to get more people to understand the fundamentals of percentages and graphs and so forth. Dear God. Okay, sorry. Oh, Jeff, you put it right there. Okay, so bar graphs. Let's say this would be identify as man, identify as woman. Bar graphs are good for if the data on the x-axis is non-numerical, normally. The book makes a couple of little distinctions. This has to represent an amount of, a percentage of, or a number of, to be what's called, so this is a bar graph. This is a bar graph primarily because this data is not numerical. Let me show you a picture very quickly. Ooh, right. You guys, this looks like a bar graph, correct? So, what the shit's wrong with you, Jeff? Your weird ass math. Okay, so let's say this is, I don't know. We ask, question, these are ages of people, and this is the number of them who have been to the Grand Canyon. Okay. What is true about the x-axis scale? What's true about the x-axis? What kind of data is that? Numerical. I love it. So the y-axis is a number of, or it could have been a percentage of. This is not a bar graph anymore. This is called a histogram. So a histogram is one where this scale has to be accurate. Now, real quick, when I made this bar graph, did it matter which bar I put first? Did it really matter which bar I put first? No, there was no order to that because it's just words. Here, does it matter that the 10 goes there and the 60 goes there? Hell yeah, it's freaking numbers. They have an order to them, so I have to have an appropriate, consistent scale. Okay. Bar graphs could represent non-numerical data. They could be whatever order they want to be in. Histograms represent numerical data that have an order they need to be in. Okay, maybe. And you guys have seen pictures like this also. You might not have realized it's officially called a histogram. Can you tell me what group had nobody that went to the Grand Canyon?
40 to 50.
People 40 to 50. I don't know why those people just, it's a weird decade they were born in. Like, heard there's a monster there. I don't want to bet. Okay. Let's see, bar graph. Oh, by the way, I don't want to do that. I don't want to do any of that. How do I make this dude go away? Start over. Yes, okay. By the way, I haven't figured out why last semester, I started using this last semester. And every now and again, I'm sure you guys remember who in my class would suddenly start replaying everything I'd written for the whole day. Still freaks me out to this day. Okay. So I'm gonna go over a couple more of these and then I'm gonna shut up and let you guys work on a little worksheet, right? Okay. Now here's what's funny to me. There is a thing that the book calls a line graph. So you have a line plot, which is better described as a dot plot, and then you have a line graph. And to be really honest, this is better described as a time series. All this is the x-axis scale is some kind of time. So it could be, for example, years. And the y-axis scale could be any kind of data. So let's say the number of EV cars owned. Yes? So then you start to plot. So this will be the numbers. Hope you forgive me, but I don't know this off the top of my head. I don't know why I picked this. So it could go like, maybe like this, and then they skyrocketed, and then they went down a little bit. Who knows? I don't know. Right? Yes?
Does the x-axis have to be time?
Normally, yes. It doesn't have to be, but that's why this is called a time series very often, is because almost always it is. Off the top of my head, I can't think of it has to be something that there's an order to. Because what this is trying to show is over time, this is why it normally is time, over time, how does something fluctuate? That's what this is trying to show. So like a histogram tries to show between groups, how does things alter? A bar graph does sort of the same thing, but with non-numerical data. A time series is over time, what's going on with this. Yeah. I hesitate to ever time say 100% of the time is this, but I can't think of a different way it would be. Now these could be like months, these could be like centuries, whatever the hell scale you're on. You're talking about climate change, it could be centuries or whatever. Okay. Not too bad, right? And then remarkably enough, you connect these. Weehaw! Woohoo! Okay. So again, just a quick little visual of how things are changing over time. Oh! Okay, you guys all with me on that? In your 125 class, how many guys remember, oh God, don't freak out. We're not gonna suddenly do this. Do you guys remember talking about Babylonian number system? Okay. That was an interesting reaction I just had. Well, don't worry, we're not gonna suddenly do them. I don't know, some of you guys liked it, some of you guys were like, dear God, I just need my Hindu Arabic. Stop it with the Babylon. Okay. Do you guys remember anything about the Babylonian number system? Do you remember their place values?
Is it the 21 or the 61?
61, yeah. The Mayans were the almost 20s. So we stole from the Babylonians the 60 minutes in an hour, 60 seconds in a minute. We stole that from the Babylonians, and they used 60 for two reasons. One is it's divisible by a lot of different things, and two, 360 shows up easily, and that of course is a year, and that's the agricultural society, blah, blah, blah. Okay. Can somebody tell me then, how many degrees, now this is gonna sound like we're all of a sudden taking this, but by the way, let me just do this, just to show you where we're headed. You guys have all seen graphs like this, yes? And they would be, ooh, if I was really slick, I would know how to do what I wanna do here, but I am not. So they're different colors, blah, blah, blah. And so each little piece could represent the amount of the budget that goes to housing, the amount of the budget that goes to education, the amount of, so yes, you guys all, you've seen this, and what is this called? It could be a pie chart. What do you think boring ass math people would call this? What shape is it?
Circle graph.
Circle graph. Okay. How many total degrees in a circle? 360 degrees in a circle, why? Why are there 360 degrees in a circle? Did there have to be 360 degrees in a circle? Nope, we just picked it. Why did we pick 360? Because I can divide 360 in a lot of ways. Could there have been 400 degrees in a circle? Of course. It was completely arbitrary. I need you to understand this. There's nothing special. Aliens didn't come and say, you will use 360 or we will look. No, it doesn't make, it's not from nature. It's just, we like the number 360. Let's use that one. Are you guys semi with me? I like to interject little snippets like that about the things in mathematics that didn't have to be the way they are. We could have chosen a different one. Anybody know something called radians? Anybody ever heard of radians? It's okay. No worries. Okay. Is that something else besides degrees that makes more sense? If I want to create a pie chart, and let's say, just for the sake of time, red, yellow, blue, green M&Ms. And I open a bag and I find 20% of them are red, 30% are yellow, 10% are blue, and what does that leave, Jeff? 40%? Can I add? I can't. And I want to represent this with a pie chart. Can you guys see how to figure out how big to make each pie piece?
Ish, yeah.
Say again?
Ish.
Ish? Like, how many degrees should the blue pie piece get? How many degrees total? 360. What percentage of those should the blue pie piece get?
36.
What percentage? We're going to catch up to you.
36.
No, what percentage?
10%.
10%. And what's 10% of 360? 36. Okay, was like, good job, John. Okay. So later this semester, I'm not going to bust them out right now because this would be a very silly little quick thing to do. Later this semester, we will be using, what's the official thing you use to kind of measure angles? Protractor. So we're going to use the hell out of some protractors and some rulers and some compasses. But for right now, I'm going to do this wrong for a second. How big is that roughly? What would you say that angle is? Well, what's this angle here? 90. So what's this look like? It's 45. I love it. So if I want 36, then I would go a little below 45, yes? Now, then what you could do, and it's hard for me to do, this is why I should be using paper for this. If you turn this a little bit and make this line, and as I turn this, you're all like, yeah, Jeff, that's helping us out. Make this line your baseline. So this will be, holy crap, what was that? That was, okay. Okay, that's neat.
He's still learning.
That is so cool, I don't know how I did that. Make this one your baseline. How many degrees should, let's go with red. How many degrees should red get? If blue gets 36, isn't red twice that?
Yeah.
So red should get twice as much, so that's,
Oh, and then you read.
no, twice 36 is 72.
72.
There you go. 72. So if you kind of like on your paper, if you rotate so that this is your new base, you can then estimate a 72-degree angle. Now, again, I'm not going to be that picky with these. You can kind of like estimate. Again, so this would look to be about a 90-degree angle. So I would do a little bit less than that. So this is blue, this is red, and then you just keep going, yes? Each one you do 30% of 360, 40% of 360. With a protractor, you can be a lot more precise. There's not that many of these problems I assign, so I just want you to get the general idea. Now, this should be a little bit bigger, but I'll. So you've seen pie charts or circle graphs before, but you might not have known how to create them. And that's basically how you do it. Just what percentage of 360 does each piece get? Let me see. All right, I think I'm almost done. And then I'm gonna let you do stuff. Last thing is called I'll shut up. We can do that last thing in a minute. So I want you guys to work on this. And I forgot to do my little picture, so I'll put you here somehow otherwise. Let me see. many people am I missing? 2, 4, 6, 8, 10, 12, 14, 16, 18, 21. I did have, yeah, okay, I had 3 people who are out. So who's everybody? Okay. So let's do this. Let's get up and move around, I think. Did I do that to you the first day?
Yes.
I did. That's not good. So let's see. Can you, let's see. I don't want to do this. Yeah, this is almost perfect. Almost, except for over there. Can you guys turn and work with these guys? You guys turn and work with these guys? You guys turn and work with those guys? Yes. You guys turn, maybe move over, you guys work together? Yes? And you guys, over here. Okay, well, can you move up here and then you turn and work together?